Hey, Science Nines, and welcome to topic 3.3 of the Space Exploration Unit, using technology to interpret space. In the last two videos, I discussed some of the technologies that are used on the side of telescopes, whether they're optical telescopes or multi-wavelength telescopes like radio telescopes or X-ray telescopes, and they obviously allow us to be able to see objects in space much closer, much larger than we would normally be able to see with the naked eye. But there are other technologies that astronomers use to help them determine things like the composition of a star. How do you determine that? How do you determine how far a star is? We talk about all these distances in space. A star is, Proxima Centauri is 4.2 light years away. Well, how do we know that? We haven't been able to travel that distance, so how can we actually calculate the distance of us to a star or to a galaxy or some kind of a celestial object in the heavens? Well, we use math. It's no different than if you go. We talked about how Kepler, back in the 1600s, he discovered how orbits of the planets were elliptical. He didn't have to leave the planet to figure that out. He just used observations made by astronomers like Tycho Brahe to basically plot the course of these objects in the sky, and using mathematics, he was able to determine that yes, all the planets were revolving around the sun in elliptical orbits. So we can use math to determine distances of objects, and we can do that here on Earth. We use a process called triangulation. Triangulation allows us to measure the distance to an object that we can't actually necessarily walk to or actually physically measure ourselves. I'll give you an example, and the one that's in your notes here is a good example. I've kind of drawn it on the board. What if you see a boat or a ship? You're on the shoreline of a beach, and you see a boat that's anchored off the shore, and you want to know how far away that boat is. Well, you can obviously estimate the distance, but there's a much more accurate way to do that. What you do is you look at that object from two different points on the beach. You can measure the distance along the beach because you can walk the shoreline. So if you were, let's say, measure, I don't know, let's say you walk 500 meters or a kilometer. Let's say we'll use a kilometer. You look at the boat from this position, then you go to look at the boat from another position, which is 1 kilometer away. So now you know the length of that side of essentially what's going to become a triangle. Because when you look at the boat from here, when you look at the boat from there, that boat is going to kind of change its angle in relation to you. Now, you can calculate the angle at which you're looking at that boat. So if you're looking, here's my 90-degree angle, and I have to lean this way, and I have to figure out my angle that I'm looking at the boat from that position, I can then basically calculate an angle that I'm looking at that boat from position A. If I move to position B on the other side of the boat, well, my angle is going to change once again. I can calculate that angle. Well, now I've got two angles, and in a triangle, if you know two angles, you know the angle, the third side of the triangle, you know that angle as well. But you also know that if you have two angles and one distance of one side of a triangle, you have everything you need to calculate all the distances that are along the edge of the triangle, as well as the distance down the middle of the triangle. So this is the unknown distance that we need to calculate. So if I can figure out the distance between point A and point B along the shoreline, that I can calculate the distance of. I can calculate this angle, that angle, and by default now that angle. Now I have all three angles of my triangle that I've created. Now I can calculate every distance either here, but this is the important one because that would be the distance of the boat to the shoreline. And that's why it's called triangulation, because we're using a triangle to calculate the distance to that object. So how does that apply in space? This is all fine and dandy. We're on a shoreline. That's a boat. That boat's like maybe a kilometer away or 2 kilometers away. The stars are a little further away. So how do we do that in astronomy? Well, what we do is we use the Earth's position. We use the Earth's position as the actual point A and point B. Now I'm going to change some diagram. I'm going to change this up a little bit. I'm going to change my little boat here. We're going to change that boat to a star. And I'm going to draw a red giant. I'm going to draw a super red giant. Here's a super red giant that's found in the constellation Orion. You might remember the name of it. It's a very famous movie starring Michael Keaton, a cult movie from the 1980s. Give you a couple seconds if you can remember it. You had to say his name 3 times. Betelgeuse, right? So here's Betelgeuse off in the far reaches of the galaxy. we are going to try to figure out how far away Betelgeuse is from Earth. Well, I need to be able to see that star from two different positions. Well, you're probably saying to yourself, well, I guess I could measure the position from, let's say, here in Morinville, and then I could travel around the other side of the world and maybe measure it somewhere in Asia, and I would have a distance. I could measure the distance between Morinville and Asia, but that's not really that big of a distance. When we're dealing with the trillions of kilometers between us and that star, that isn't going to be a long enough distance on this side. We need to come up with a bigger distance. Now, the biggest distance that we can on the Earth is, you got to remember, the Earth is not stationary. That's the key to this. The Earth is always spinning around the sun. Now, do we know the distance of the Earth to the sun? We do. It's 1 astronomical unit, right? So we know that distance. We're guaranteed to know that distance. So if I were to see Betelgeuse, let's pick 2 dates of the year. These are dates you are also familiar with. Remember the solstice dates or the equinox dates, right? Those are the dates where the sun is either at the highest point in the sky or the lowest point in the sky. That would be the solstice, right? The summer or the winter solstice, or the equinox, which is the start of spring and fall, where you have equal amounts of day and night. But those dates are also significant because the Earth is on exact opposite sides of the sun on those particular days. When the Earth is on December 21st, it's exactly on its orbit. It would be like over here in its orbit. Then it's going to spend its time. It's going to get to the spring equinox down here. It's going to get to the summer equinox over here. The fall equinox over here. Back to the winter solstice over there. So if I can measure Betelgeuse on one of those opposite days, and it doesn't have to be the solstice dates. It could be any 2 days that are opposite from each other in the Earth calendar. They just have to be roughly 182 days apart, or roughly 182 and a half days apart, because that's the length of the year. And astronomers know this. You now know the distance of one side of your triangle. So if this would be the Earth on, let's say that's the Earth on December 21st. And this would be the Earth on June 21st. Let's just use the solstice dates to kind of make it easy for ourselves. Well, I now know that my distance, and right here would be the sun. The sun would be right here in the middle. Here's my sun shining down on the solar system. Obviously, my image is not to scale. Sorry about that. But we now know that the distance from here to the Earth and to the sun is 1 AU, and the distance of the Earth to the sun on this side is 1 AU. So we technically know that this side of my triangle now has a distance of 2 astronomical units. And that's about the biggest distance that we can work with if we're fixed here on the Earth. Like, we can't really have a larger distance on that bottom side of the triangle. And what astronomers are going to find, and what you would find if you did the same thing, if you were to take a picture of Betelgeuse on December 21st and took a picture of Betelgeuse on June 21st, you would notice that that star would be slightly different in position in the sky relative to other stars around it. The star hasn't moved. We've moved in relation to the star. Now, technically, the star could be moving away or toward us. We'll get to that in a couple seconds. But it's not like the Betelgeuse is doing this every 6 months. It's not. We're the ones that are moving around the sun. So what we see is a relative position change of that object. Another example would be, and you can do this at home right now, take your finger out from you, and you're going to basically do the old, I'm going to move my finger trick here. I'm going to basically do this. I'm going to cover one eye, look at my finger, and then cover the other eye. What you're going to notice is your finger is moving position relative to which eye I'm looking out of. This would be the Earth on December 21st. This would be the Earth on June 21st. And this finger would be Betelgeuse. So you're seeing that what we call this is parallax. This is a concept called parallax that is huge in astronomy. This is one of the fundamentals that allows astronomers to figure out the distances of objects relative to the Earth. And if you want to get some more information on parallax, watch the video here. Great little summation of parallax if my description didn't make a lot of sense there. But that's essentially how we can calculate the distances of objects that we have no way to get to, at least not yet. I mean, maybe at some point in the future we can develop some kind of, I guess above light speed travel, warp speed. Although technically, according to Einstein, that the speed of light, 300,000 kilometers per second, is the absolute fastest anything in the universe can go. So technically, if you're a fan of Star Trek, if you're watching Star Trek Discovery or maybe Picard, any of the old series, warp speed technically, theoretically, is not possible, at least according to Einstein. But that allows us to see these objects and not just be able, not see them. It's going to allow us to actually calculate the distances of these objects. So that's one thing that we can do. We can use mathematics to help us calculate the distance of stars. Now, what else can we find out about these stars rather than just looking at them? We can also calculate what they're made of. We talked about the sun being mainly made up of hydrogen, and it's fusing the hydrogen into helium. Most stars are comprised of hydrogen. But as this fusion reaction kind of plays out, as the star gets older, the star will begin to then fuse the helium into larger atoms, and then those larger atoms into even further larger atoms. So by determining the composition of what elements are actually present in the star, we can actually calculate roughly how old the star is based on how much hydrogen it has compared to other elements that are found in that star. Well, how do we know what the elemental composition of the star is? It's not just winking at us and saying, hey, I'm made of hydrogen. I'm 85% hydrogen. I'm 17% helium, and just a little bit of sweet on the side there. It's not doing that, but in a way it is. What the stars do is they're emanating light. They're emanating electromagnetic energy, like I talked about earlier in this section of the unit. They're emitting visible light, X-rays, gamma rays, UV rays, all these different types of electromagnetic energy. And if we can see that energy coming toward the Earth, visible light, because we see that light from that star, we can actually measure the wavelengths of light that are actually coming from that star. And we can use something called a spectroscope to do that. It's a little device that basically measures specifically which wavelengths are coming through. Is there more red light coming from the star? Is there more blue light coming from the star? Which specific wavelengths are the dominant wavelengths coming from the star, which are being emitted from the star? So by doing this, we can compare the data from that spectroscope from known data from elements that are present here on Earth. So scientists have basically cataloged if I bombard hydrogen with energy and it emits light, what pattern am I going to get on a spectroscope? There's a specific pattern that is unique to hydrogen. There's a pattern that's unique to helium, to all the elements. So the scientists have done these experiments here on Earth. They know which specific wavelengths are emitted by different elements. Now, when they compare this data to what they're seeing from any star in the universe, they can overlap these, what I like to call wavelength fingerprints, for lack of a better term, and they can see if they have a match. So, they can say, well, we're seeing that it looks like it's emanating hydrogen. It's also emanating maybe some boron or helium or whatever. So these patterns that are being, picked up by these spectroscopes are unique. And each star has a unique fingerprint, but we can compare these to the unique fingerprints of these wavelength the wavelengths of light that are being emitted by elements here on Earth. So this allows us to basically calculate what stars are made of using this process called using a device known as a spectroscope. And you'll learn more about this if you take Science 30. We discuss this in much greater detail. There's different types of spectra that can be created. There's full wavelength spectra. There's a bright line spectra. There's dark line spectras as well. We're not going to get into that specifically in grade 9, but we will eventually get to this more if you decide to take Science 30 in grade 11 or grade 12. Now, what else can these spectrum or these spectroscopes also tell us? Well, we know what the fingerprints look like for elements here on Earth. We know that specific wavelengths are going to be emitted by, let's say, hydrogen or helium. But what sometimes will happen is, let's say I've got a pattern from a star, and this would correspond with the pattern of this element and this element over here. Like those two would be for, let's say these would be for hydrogen and these two would be for helium. But what sometimes scientists will see when they look at a star is they'll see the pattern. The pattern is actually correct, but the pattern is actually shifted. It's actually shifted either more toward the red end of the visible light spectrum, or it's shifted over to the blue end of the visible light spectrum. Now, why is this? Well, you might have heard of something called the Doppler effect. And the analogy I would use is if you hear a race or a car that's racing towards you, As the car approaches you, the sound the car is making is a higher pitch sound. As the car kind of passes you, you're going to hear a lower wavelength sound. So, for example, it would be something like this. You'd hear the, so let's say this is the car coming toward me, and then it's going to go past me this way. So you'd hear something like this. You hear that. It would go like something like that, right? Like a motorcycle. That's a really good example, would be a motorcycle. So you're hearing that as it goes past you, right? Well, why is that? Well, higher pitch wavelengths, higher frequency wavelengths of sound make higher pitch sounds, right? So these are higher frequencies, tighter wavelengths together as the motorcycle is moving toward you. As the motorcycle passes you, you get lower frequency sounds, which are wavelengths that are spread out further apart. And that's the Doppler effect. As you can see in the diagram here, as an object moves through the air on Earth, the sound waves in front of that object get compressed because it's actually pushing up against those wavelengths in front of it. So any sound in front of the object is going to sound, it's going to have a higher frequency because the wavelengths are tighter together. As the object passes you, the wavelengths behind it get stretched out. They get longer. It's almost like a draft behind the vehicle. Now you're going to hear lower wavelength or lower pitch sounds. The same happens if an object is moving through space, but not with sound. Now we're dealing with wavelengths of light. So how do we perceive that? Well, as I mentioned, this spectrum that we see in these spectroscopes will shift either to the blue or to the red. Well, let's think about that for a second. The red wavelengths are longer wavelengths of light. Blue wavelengths of light are actually shorter. So if I see a pattern in a spectroscope that's shifting toward the blue, I'm seeing the wavelengths of light in front of an object that's moving toward me. So if I were to see a blue shift in a spectroscope on a star, that would indicate to the astronomer that that star is actually moving toward the Earth. If I saw a shift in the spectrum toward the red side of the spectrum, I'm now seeing the longer wavelengths of light, the wavelengths that are stretched out, that would be behind an object that's moving away from me. So if I see a red shift in that spectroscope, that indicates that the object is moving away from the Earth. And most times, what do you think we're going to see? What are we going to see more? We're going to see more red or blue shifts. Pause me if you need to think about it. I'm going to give you the answer here in a second. Are we going to see more red or blue shifted stars, do you think, in the sky? Well, the answer is we're going to see more red shifted stars because the theory is the universe right now is expanding. Everything is moving away from everything. It's very rare that scientists see blue shifted objects in the sky. In fact, it was just very recently that scientists saw the first blue shifted galaxy. Pretty much every galaxy that scientists have looked at in the stars outside of the Milky Way, they're all red shifted because all these galaxies are moving away from one another. But they did find one galaxy, I think it was in 2019, if I'm not mistaken, that actually is a blue shifted galaxy. So they're very rare, but they are out there. But for the most part, pretty much every object that astronomers see in the sky, they expect to see a redshift because these objects are, in fact, the universe is right now in an expansion phase. So everything technically is moving away from everything else. But there's always an exception, which again, I just mentioned, there's at least one blue shifted galaxy out there. I'm not sure about the stars, but most stars are going to be redshifted. One thing to keep in mind, this has nothing to do with the temperature of the star. You could have a blue star that's a hot star that could be redshifted. So please don't get confused between the temperature that I mentioned earlier, how we had blue stars that were hotter and red stars that were cooler. When I say blue shift or red shift, it's not about the temperature of the star. It's talking about the direction of the motion of the star relative to Earth. And that's basically redshifting and blue shifting. And that's our topic for today. We're done. Topic 3.3, just like that. Here's your homework for today. I'd like you to complete questions 1 to 7 on page 454 of the textbook. And I'd like you to complete questions 1 to 9 on page 455 in preparation for your upcoming quiz, which is going to cover topics from space exploration from 2.1 all the way to today's topic of 3.3. That's it for today. And next day, I'm going to complete the space exploration unit. And in fact, I'm going to complete the Science 9 course. One more video left to go. I'm going to quickly run through topics 4.1, 4.2, and 4.3 of the Space Explorations unit here in Science 9. Can't wait. We're going to finish this sucker up in style. Thanks for tuning in, everybody. Have yourselves a great day, and we will see you soon.